Hi, this is a continuation of the previous video on the problem of class imbalance, and today we'll be looking at the solutions to this problem. Now, our first strategy involves modifying the loss function, specifically the binary cross-entropy loss function, which is pivotal for binary classification tasks. Now, to give you a brief recap, this loss function evaluates the prediction error of a model, and it is especially common in applications like classifying X-rays into normal and abnormal categories, as we have explored earlier on. Now, here is a binary cross-entropy formula, and in this setup, y is essentially our target variable, which is 1 for abnormal X-rays and 0 for normal ones. And p here is the predicted probability that an X-ray is abnormal, and this is generated by the model. And typically in an imbalanced data set, the frequent normal cases tend to dominate the loss calculation, which skews the model towards perhaps predicting the majority class predominantly. Now, in order to counteract this imbalance and solve this problem of class imbalance, weighted binary cross-entropy loss functions introduce class-specific weights, wherein WP is essentially the weight for abnormal cases, and WN is the weight for normal cases, which in the case of a specific video is the majority case. And weights are generally computed as, for instance, for the case of WP, the number of negative or normal cases above the total. So, for example, in a data set with approximately 95,000 normal X-rays and 5,000 abnormal X-rays, the weight for the abnormal cases would essentially be 95,000 over 100,000, while the weight for normal cases would be 5,000 over 100,000. And this means that the model will generally assign 18 times more importance to the abnormal cases during training to ensure that it learns effectively from these rare cases from these minority classes. And one other critical approach to addressing this problem of class imbalance is through the resampling techniques. Now, these methods do not just modify the model itself, but rather adjust the composition of the data set in which the model learns from. And the goal here is to essentially create a more balanced data set, which can lead to a more accurate and equitable model prediction. And there are mainly two techniques under this idea of resampling, and this is oversampling and undersampling. Now, let's first begin with oversampling, and this is a technique wherein we increase the number of instances of the minority class, the abnormal cases in our example, in order to match the majority class. And this is typically achieved by duplicating the existing abnormal samples until both classes have an equal presence in the dataset. Now, this method ensures that the AI model is exposed to enough cases for each sort of class, which helps it to learn and identify features associated with abnormalities more effectively, as in the case of this specific example. And it is particularly useful in situations where the minority class is very small, and this is often the case in many medical data sets where the abnormal findings are rare but very critical in order to detect. And some of the advantages of this technique of oversampling include, first of all, being able to reduce model bias, which I suppose is essentially like the goal of oversampling. Because you're balancing class distribution, oversampling essentially prevents the model from overlooking the minority class. And it also enhances learning on small data sets. Now, this is kind of in the sense that because it allows the model to train on limited data, it allows it to train better on limited data by artificially inflating the presence of rare cases, which generally ensures these important scenarios are just not ignored during the process of training. However, some of the general disadvantages of the technique of oversampling include this risk of overfitting. Because we're repeatedly using the same samples, there's a significant risk that the model will learn from these samples by heart rather than just developing a more generalizable pattern by looking at these cases and just instead looking and experiencing these cases individually, which can lead to the model learning these cases in a personal basis rather than just finding a generalizable pattern. And one other risk involves increased computational load. Because more samples mean more data for the model to process, this can lead to longer training times and generally increased memory requirements. Conversely, we can use this technique of undersampling, however. And this technique of undersampling generally involves decreasing the number of instances in which the majority class appears. And this method generally reduces the presence of more frequent normal cases, thereby balancing the data set and bringing the numbers closer to a sort of an equal number. And the technique of undersampling definitely does have its benefits and pros and cons. Its advantages generally include the fact that it can mitigate the majority class bias, again achieving the sort of goal that it intends to achieve, vice versa to the oversampling technique. And also it allows for efficiency in large data sets. Because in lots of large data sets, majority classes can often be redundant or they can be overrepresented, and the technique of undersampling in this case can reduce training time and resource consumption without a significant loss in the sort of information or the sort of generalizable patterns that the model can extract by studying the data set. However, some of the general disadvantages of the technique of undersampling include loss of information. And loss of information is in the sense that because we're removing samples from the majority class, important information might actually be discarded, which could be detrimental to the model's ability to generalize by finding even broader patterns. Also, one other disadvantage includes the risk of losing variability. There's a danger that reducing the number of normal cases might actually remove the critical variations within the normal class, which makes it harder for the model in order to learn the full spectrum of what actually constitutes a normal result. Now, to wrap everything up, both weighted loss functions and resamplings are both just potent techniques in order to manage this problem of class imbalance. And they both definitely have their own pros and cons, and the choice between them should be guided by specific requirements of both the data set and the model. And in our next video, we'll explore 2 additional methods in order to solve this problem of class imbalance, which is data augmentation and adjusting decision thresholds.